Okay, today we'll solve GATE 2022 question from mathematics. This is a question number 24 from topology. So let xn be R for each n belongs to natural number, and why is this the product of xn where n belongs to natural number, and we have n row y with the product topology where each xn is the Euclidean topology or of R. And define this delta. This is the diagonal, means all the term x where x is real number. This is the diagonal set. So this we have induced with the subspace topology from Y. Then 4 options are given. You have to check that delta is open in Y, its delta is locally compact, delta is dense in Y, or delta is disconnected. Which one is correct? You have to check. And for this question, this is the NPTEL reference. This you can look into it. Okay, so let's try to solve this one. First option, delta is open in Y. The option number A. So we'll show that this is not true. We'll show that delta, which is the diagonal set x such that x belongs to R, is not open in Y, or Y is this the product of all R cross R cross R, where this is with product topology. So suppose, assume, we'll prove this by contradiction. Suppose delta is open in Y. Then what will happen? So if open set is open, it's saying that if every point is an interior point, means each point has a neighborhood, open neighborhood, which will is entirely contained in these sets. Means, so which implies every point, suppose let's denote it by x bar, this x comma x. So every point will belongs to some open set U, which is entirely contained in delta, right, where U is open in Y. And what is Y? This is the product of xn. N belongs to natural number, or xn's are basically the real line for all n. So U is a open in this product space, so means U, and with respect to product topology, so therefore how U will look like? U will be some U1 cross U2 cross dot 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 UK cross, and after finitely many, these are all R, right? So for some K, where this UI for I equals to 1 are open in R for I equals to 1 to K, right? So this is the basics open sets in the product topology. Now we claim that this U1 will be singleton X. Claim this U1 will be singleton X. So suppose if not, then what will happen? If not, then so there will be some another element, there exists Y in this open set U1 such that Y will be not equals to X, right? There will be exist another point different than X, other than X. So if there is such y, then because this u is entirely contained in delta, so u1 if it is contained, then take this point, take y, x, x, first quadrant will take this, so this will belongs to also, right, this will belongs to u1 cross u2 dot 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 uk cross r cross dot dot dot, right. So this is the u which is again contained in, and this is contained in delta, right. But this type of points does not contain in delta, right. This is a contradiction, this is not true, as y not equals to x, right. This is not true, as y not equals to x, right, because diagonal contains all the points which has all the same coordinate. So this is not true, means this u1 does not contain any other point other than x, so therefore our claim is true. Therefore u1 is basically just singleton x. And what is u1? So these ui are the open sets in R, right, and we have get u1 to be the singletons, which means, which is same thing as saying that u1 is, which is this singleton, is open in R. But this is not true, right? This is a contradiction. But why this contradiction arises? Because we have assumed that delta is open in Y, right? So which is a contradiction. So we have arrived this contradiction because of the assumption that this diagonal delta is open in Y. Therefore delta is not open in Y. Okay. So option A is not correct. Delta is not open in Y. Now let's check in option B. It's saying that delta is locally compact. Okay. So we'll show that this is true, means delta is locally compact. Let's recall the definition of locally compact. So a space X is called locally compact if there exists an open set U and a compact set K such that X belongs to U which is contained in K, right. So each point has a neighborhood which contain an open set, or each point is contained in open set which is again contained in a compact set, right. So this is the definition for locally compact. And now we will use one more fact. Let's write it, or result. Saying that it means locally compactness is a basically topological property. What is this? locally compactness is topological property. What is the meaning of this? Means it preserves a local compactness is preserved under homeomorphisms. Means if f from some space x with topology tau 1 to x with respect to topology tau 2 is a homeomorphism, and x comma tau 1 is locally compact, then y comma tau 1 is locally compact. Right. So if there is a homeomorphism between two different spaces, so this is y. Then if one is locally compact, then other one will be locally compact also, if there is a homeomorphism. So this is the meaning that this is a topological property. So you'll show that this delta is homeomorphic to the some different space which is locally compact. So therefore this will be again locally compact. So let's claim. So R is basically homeomorphic to this delta, or R is homeomorphic to delta. Our delta is given the product topology, right? So what is, let's define this map R to delta, which is this basically the diagonal. So x goes to this x comma, right? So if we can show that this is okay. Now if if we can show that this is a homeomorphism, then we can, so let's check the homeomorphism property. So let's use one theorem here. So for that homeomorphism, we have to show that f is continuous, this is bijective, and inverse is also continuous. Let's write down one theorem. For the continuity, we will use this theorem. F is continuous. So this is continuous. This is one theorem for the product topology, that if let f from A to some product space alpha belongs to J x alpha, or this is given the product topology. And suppose f of A it sends to this f alpha A, where alpha belongs to J, and where each alpha is a map from A to x alpha. Then f is continuous if and only if each coordinate functions are continuous. Each functions f alpha is continuous. Right. So we'll use this theorem to prove this one. So what is f in our case? F is a map from basically R to this space, right? R to delta f of x, which is x comma dot dot dot, right? So let me denote it that suppose f1x, f2x. So fnx is basically x for all n belongs to n, and fn is a map from, so note fn is a map from R to R. Fn of x equals to x. So this is clearly continuous for all n. This is basically identity map. Each fn's are continuous. So by the above theorem, f is continuous. So f is continuity is fine. Now bijectivity is also fine. F is bijective. F is bijective. Right, because f is 1 1, f is 1 1 basically. Suppose f of x equals to f of y. So what will happen then? X dot 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 equals to y. So each coordinate will be y, which implies x equals to y, right? And why f is onto? F is onto also, because this is by definition onto, right? If you take any point, it will look like some. So let's z in this delta, which implies z will be some y dot dot dot. So then f of y will be z, right? Implies f is onto. Y is in R. So bijectivity is fine. Now inverse. So inverse is well defined. Then f inverse is a map from delta to R. It will basically take this x dot 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 to x. So f inverse is also continuous. How to solve this one? So for that, this you can see basically that now define, let's the projection map. So let's define. Suppose projection from, suppose let define pi 1 from product of xi, I belongs to sub index set, to x1. So what this is the product topology. So pi 1 is projecting this pi 1 of x1 x2 dot 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 this, it will only project the first coordinate x1. Then pi1 is continuous, then each projections are continuous, then pi1 is continuous. Why? Because pi1 inverse of, suppose take open set u1, it will be some u1 cross this x2 cross x3, right, which is open in this, right. xi. So pi1 is continuous, and basically this F inverse is restriction of this projection to, now in our case here F inverse is basically the restriction of pi1 to this set delta. So pi1 basically defined from xn here, so let me denote these are to be xn, then it will be because consistent with right. Then pi1 basically the F inverse is basically restriction of pi1 to this, so this is basically map from delta to r, and as if pi1 is a continuous and restriction of a continuous map is continuous, so this is again a theorem. If f from x to y is continuous and A is subspace of x, then f restricted to A, which is mapped from A to y, is also continuous. So therefore this F inverse is also continuous. Therefore F inverse, which is mapped from delta to R, is continuous. So we have got that F is a continuous, F is bijective, and F inverse is also continuous. So F from R to delta, so this is this set, what is the map, x goes to this x comma this is homeomorphism. Now as we know that R, this is locally compact, as we know R is locally compact. Why R is for any point, suppose, so why this is locally compact? For any A in R, A is contained in some CD, right, which is again contained in C to D. And this is compact and this is open, right? and as delta is homomorphic to R, so therefore delta is also locally compact. Also delta is locally compact. By the earlier theorem, this theorem, right? This result, by earlier result. Okay, so this is the option B. So option B is correct. The delta is locally compact. Now option C, this is saying that delta is dense in Y. Let's check this one, that delta is dense in Y or not. So we'll show that delta is not dense. We will show that delta is not dense in Y. Okay, so here we need a one result. Let me write. So we'll show that delta is closed first, then we will show that this is not dense. So for this we will suppose let X is housed up. So let here we have what we have, the delta is closed if and only Y is, suppose this product of n belongs to n, this is xn, where xn is same, right? X for all n. Then suppose this is with respect to product topology. Then delta, so let's define first the same as early defined, diagonal. Then delta is closed in Y if and only if this X is housed up. Right. So in our case, this is the R. So here Y is basically this product of n is xn, and xn are basically R for all n, and R is housed up. Therefore delta is closed. Now we will show that this delta is not dense. So what is meant by dense? So let me write the definition. So suppose X is a topological space, S set, suppose C is dense in X if C closure, this is a closure of C, equals to x, where this is the closure of what is the means the smallest closed subset containing C, or intersection of all closed sets containing A. Intersection of all closed sets containing C. So a set is called dense if closure is equals to the whole space, whole topological space X. And also this is one result. If A is closed, then closure is the same of that set. This is one result. So you have to show that delta is, we will show that delta is not dense, means we will show that delta bar is not the whole Y. Now we have proved that delta is closed in Y, as we know, we have shown delta is closed in Y. So delta bar is same as delta, and we'll show that this is not equals to Y. And note, take some point, this point 1 2 3 4 dot 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 like this. So this does not belongs to in delta, right? So this is does not belongs to delta, but this is in the Y, and this, but this 1 2 3, this set is in Y. So therefore delta bar, which is again delta, not equals to Y, right? Which implies delta bar is not equals to Y, which implies delta is not dense in Y. So therefore option number C is not correct. Delta is not dense in Y. Okay, now option number D, it's saying that delta is disconnected. Again we'll solve so that this option number D is also not correct. So D, we will show delta is not disconnected. Means we will show that basically delta is connected. So what is this means? Basically we will show delta is connected. Let me recall what is the definition of connected. A space X is said to be connected if there does not exist a pair U B of disjoint non-empty open subsets of X whose union is X. So this is the definition of connected. And if X is not connected, we will call, otherwise X is called disconnected. Okay. So we'll show that this diagonal set delta is connected. So for this we will again this theorem. So let me use this theorem. Let me call it this theorem to be star. Which is theorem from part B. From theorem star of part B we know this map, there we have defined it from R to delta. This is the diagonal set. X goes to this is continuous. Right, so we know F is continuous. And this is basically the delta is the image of R, right? Also note image of F, this is the image of R under F. So this is the delta. And let me write one more result, so theorem. So we have to show that delta is connected, right? So here we know that AP is continuous and we know R is connected, right? And there is one result that this continuous image of a connected set is connected. As R is connected, so delta will be connected, right? So this is that the result I am writing, that continuous image of a connected set is connected. So therefore using this one, as we know R is connected and delta is basically image of R under F, and F is continuous. So this is basically continuous image. Under F, which implies delta is connected. So therefore option D is also false, right? So therefore what we have got, the delta is open, so this is not open, this is A is false. Delta is locally compact, it's true. Delta is dense in Y, it's not true. Delta is not dense in Y. Delta is disconnected, it is also not true. So only B is true, that this diagonal set delta is locally compact. Okay.